Hey class. Alright, we've looked at synthesis, then we've looked at decomposition, we even looked at combustion. Hey, what's next? Well, we have the displacement reaction. There's two types of displacement reaction. Today, we're going to look at the single one, okay? So those single individuals that we're talking about out there, alright? This is for you. So we have single displacement reaction. They're also known as single replacement reaction. You know, just really not a big deal in terms of what you want to say. But let's fill in those blanks. So in a single displacement reaction, one element replaces another element in a compound. Definitely. Exactly what you're seeing right now at the bottom. This is the general reaction of what a single displacement reaction is all about, where you have some sort of element X displacing the compound of YZ. Okay, so what happened here is that Y gets kicked out of this relationship with Z. Y being all alone now, as you see, and what you'll also see is a compound known as XZ. Alright, where X and Y are, of course, elements, seeing this general reaction is trying to show us, and YZ and XZ are compounds. Now, one thing you need to note, let's write a little note right here, okay, is that metal displaces metal. Okay, so you get to imagine the fact that X and Y are metal, or X and Y are non-metal. So let's write that down too, okay? Because non-metal displaces non-metal. You won't have a metal displacing a non-metal in a reaction like this. That would be weird if you think about it, okay? Because if you think the fact that if this was a metal and this is a non-metal reacting with a metal, if you have a metal displacing a non-metal, wouldn't this metal be in a compound with this metal? I mean, that's kind of strange to think of M&M like that, but that's not the way it's supposed to be, okay? There's always metal displacing metal, non-metal displacing non-metal, and that's how it works. Always. So let's take a look at some examples. The first two, okay, we did for you, where you are seeing iron displacing copper to be with sulfate. Just giving you iron sulfate. Sad part is, by doing that, by displacing the poor copper here, copper is now all alone, all by himself. But of course, he doesn't mind that, obviously. Now, one thing you need to keep in mind is that this reaction is not the only thing that you're going to... Basically, this compound is not the only compound that you will see. Because iron, we know, has multiple charges. In this case, this iron is acting as a 2+ iron to do this. I mean, why can't this be a +3 iron? And the answer, of course, is that it can. Of course it can. So let's write another one of these things. Copper, iron can react with copper to give you copper. And in this case, an iron sulfate that is based on iron 3, which is, of course, your iron 3 sulfate. That can happen too. I mean, nobody said it cannot, right? And don't forget to balance these things at all time. Okay, I think this is balanced. Yeah, it looks pretty balanced. So make sure you do that, and make sure you recognize the fact that iron has multiple charge. Iron in a single displacement reaction will displace the other metal, leaving this metal, all alone. And this, of course, iron is hooked up with the sulfate that you see right here. Okay. All right. B is also something I did for you. This time, of course, we're seeing copper reacting with silver nitrate. Copper displacing the silver. Okay, not copper displacing the nitrate. That's not going to happen. Copper is going to displace the silver because metal displaces metal, leaving silver all alone. Copper will now bond with the nitrate, as you see here with copper 2 nitrate. Yet again, this copper is acting as a copper 2. Does it always have to be copper 2? I mean, there's also copper 1 that exists in this world, right? Well, copper 1 can also play. Okay? Giving you, of course, Ag again, plus, in this case, copper 1 nitrate. Okay? Again, something to keep in mind, because this copper right here can act as copper 1 or copper 2. It's pretty much random. All right. After getting these out of the way, let's do C and D, because this time I did not give you the answer, so I'm banking on the fact that you can figure it out, right? Now, magnesium reacting with hydrogen chloride. Well, magnesium is going to displace a metal. But, oh no, there is no metal here. Hydrogen is not a metal. Chlorine is not a metal. So who is he going to displace? Well, the logical reason here is that he's going to displace hydrogen. Okay, even though hydrogen is not a metal, but hydrogen acts like a metal. Being in group 1, give him this idea that I like to lose electron too. Okay, sharing with electron with chlorine, I'm actually getting the less end of it. So if magnesium going to come and displace HCl, he's going to displace the H and not the Cl. So remember that, okay? H sort of act like a metal at times due to his ability to lose electron. I mean, chlorine doesn't like to lose electron, right? So therefore, this is what's going to happen, okay? So what you're going to get here is MgCl2. Remember, cross rule always applies. Mg is a 2 plus ion. Cl is a 1 minus ion. When you cross it, you get MgCl2 plus H. No, not just H. H cannot exist on its own. That's ridiculous. You never, if H were to exist on its own, it may be in a form of H+, but why would you have an ion being displaced in the first place? If H were being displaced, it's going to be displacing as a gas, H2. Okay? You're never ever going to see H neutral being alone. Okay? Later on, you may see H+ when we talk about acid and base reaction, but you're not going to see H all by himself. It's going to be in the form of H2. So, something to keep in mind, very important. Hey, the funny thing is I gave you 2 here because I kind of knew what this is going to be, so therefore this is all balance. Let's take a look at this. Okay, lithium reacting with water. There's a reason why I didn't do H2O. Because if I were to do H2O, a lot of you may think that Li is going to displace both of these H's. A lot of people would think that way. As a result, you get lithium oxide plus hydrogen, right? Right? Lithium oxide plus hydrogen, because that's what the case was the case. That's exactly what you're going to get. But that's exactly what you're not going to get. That is wrong. That's why I decided to, instead of writing H2O, I wrote HOH. Because lithium is going to displace one of these H, and not both of those H. As a result, what you are going to get is a base called lithium hydroxide plus H, no, not H on its own, remember, H2. That's why it's not a good thing to leave these alkali metal, on its own. Okay, you wouldn't take an alkali metal and put it, on your desk, on a table, exposing to the moisture in the air. Because if you think about it, these guys actually react with water, and they react with water pretty spontaneously. And as a result, you get a base. Bases are pretty terrible things. It's corrosive. Not just that, but you're making hydrogen gas that are also explosive. So alkali metal in an area where there's a lot of moisture will only give you bad and bad things. Double bad. DB. Okay? A corrosive base and an explosive gas. Maybe later on I'll demonstrate this to you. Okay, using sodium, because sodium, when you put that in water, you get the same thing. You get sodium hydroxide and hydrogen gas, where you'll see a little bit of that explosion in front of your eyes. Or you can just YouTube it anytime you want, on demand. Okay. All right, hopefully you understood, the idea here, and just understanding the fact that this is exactly what happens. All right. There's I think there's a little bit of an error here. Okay. Well, not really an error, but you think about balancing in this case. You might want to put a 2 here, because there's some reason there's already a 2 there. All right, and I should put a 2 there as well. Okay, so don't forget that. All right, there's single displacement reaction. Yes, no, not really, because right now we're under the assumption that all single displacement reaction happens. No, that's not true. Not all single displacement reaction will give you products. In this case, we assume it is, and it is. But there are a lot of reaction where you don't get products. X can't be running around saying that, hey, I want to displace Y so I can hook up with Z because I am big and bad, just like that. No. Y may say, who are you, X? Who do you think you are? You just gonna come here and displace me just like that? You're gonna have to have potential, man. Do you have potential to displace me so you can hook up with Z? Because if you don't, this is not gonna happen. So let's take a look at the next page right here. Okay, I'm gonna show you this thing called the activity series. Now, for you students, you guys also have the activity series right here in your IB booklet. Okay, I don't remember what section this is, but this is one of the sections where the activity series of metals are presented to you. All right, now how do you read this? It's very simple. The the stuff on top, I guess, okay, the stuff on top is more reactive than the stuff at the bottom. Just think of that way, okay? Much more reactive goes on top. So this works with single displacement. In fact, this is exactly what you would predict your single displacement by if a reaction were to occur or not. So let's say BA, okay, BA versus Zn. Which one is higher in the activity series? So if you look here, there's BA right here, okay, and there's Zn right here. BA is above Zn in this series. In this case, BA will displace zinc. Okay, BA will displace zinc. What about calcium versus cesium? Can calcium displace cesium? Well, let's take a look at where they're at in the activity series. Calcium is right here. Cesium is right here. Can calcium displace cesium? No, because cesium is higher in the activity series. In other words, if calcium were to displace cesium, calcium needs to be more reactive. Calcium needs to be more attractive. But in this case, it is not. Not gonna happen. So that's how you read the activity series of metals. Now, let's go back here, okay? I would advise you to use this just to get used to looking at this rather than this. It's really the same thing, but this one has more. So when you come across more problems later, this will help you a lot more than the one in your course pack. Okay? But let's fill in some of these blanks here. Any metal will replace a metal in a compound only if it is above in the activity series. For example, magnesium will replace nickel in a nickel compound, right? Because magnesium is higher in the activity series than nickel. Lead will not replace aluminum. So lead will not displace aluminum because aluminum is below. Okay? Sorry, lead is below aluminum. So lead will not be displacing aluminum in an aluminum compound. All right? The concept of electronegativity also play a role here to create this electrostatic series. Okay? Because you can think of it as this. You go for a metal, the lower the electronegativity, the more reactive the metal will be. Now, that's kind of obvious if you think about it and think hard about it. Electronegativity means the atom's ability to attract electrons, okay, or love an electron. As a metal, metals don't really love electrons that much. Metal likes to give away electrons to become a positive ion, right? So the more that I want to get rid of my electron, obviously the lower in electronegativity I am. The lower in electronegativity I am, the more reactive I am. Hence, that's why we always say francium is the lowest in terms of electronegativity, what that means is that francium as a metal is the most reactive because he can easily get rid of that electron. Right? So that's why we say that for metals, the lower the electronegativity, the more reactive this metal is going to be. So if we were comparing lithium versus sodium versus potassium, which metal is the lowest in electronegativity? Well, by looking at the trend right here, by looking at this right here, is potassium. So that's K. Which means the more reactive metal in the three is also K. Okay. Let's go back to this. That is strange. This is strange. Why is lithium all the way up here though? Because if you look at the electronegativity table, lithium has the highest electronegativity. Well, not the highest, but out of the three right here, out of these three, lithium is the highest electronegativity. We just said the lower you are as a metal, the more reactive. It seems like lithium is the most reactive. Why? Well, the reason is kind of strange, and it's quite ambiguous at the same time. The reason that lithium is at the top of the activity series, meaning that nobody's going to displace this guy, is due to its behavior as an aqueous reaction, reaction with water. When lithium reacts with water, it forms an acid, and that is something that is very stable and very willing to be done. Okay? Due to the fact that lithium is very small. It only have a value of n equals to 2. The lithium ion interacts very well with water to form very, very stable things. So that's why he's on top. Okay? Now, that's pretty much the reason for you. You just need to know how to use the electrostatic series. Okay? You just need to know how to use this electrostatic series. That's the most important part that you need to know. So let's do these questions. Okay? So here's single displacement reaction. We have zinc trying to displace lead. Let's do the reaction first. Okay? What you're going to get, of course, is zinc nitrate. Remember, cross rule apply. Okay? Zinc is a +2 metal. And we have lead all alone. The question is, will this happen? Can zinc displace lead? Well, let's take a look at the activity series. Let's find zinc. Let's find lead. There's zinc right here. Let's use a pen. Oh. There's zinc right here. And there's lead right here. Looks like zinc can, because zinc is above lead. So therefore, this reaction will happen. And well, zinc is gladly to leach lead out of this reaction. Notice what I said there, leach, because that's exactly how you leach a metal out of a compound. So you have a lead nitrate compound, and you really, really want to get some lead. I don't know what you're going to do with this. So to leach lead out of a compound, all you have to do is pick an element that is higher in the activity series. So in this case, take some zinc. Okay, take some zinc, put it into a solution of lead nitrate, and you'll notice that there will be a color change because you're no longer going to get lead nitrate, but what you'll get is zinc nitrate because lead is being leached out. Okay? That's a very important thing, especially when you're into mining things. All right, let's take a look at the next reaction. The next reaction says silver reacting with copper sulfate. So I guess you're going to get silver sulfate, right? Plus copper being all alone. Will this happen? Will silver be able to leach copper? Well, let's take a look at where they're at the activity series, right? I don't know why I keep pressing that button. So I have silver right over here. And look, copper is just right on top. Hi, neighbors. Can silver leach copper? Oh, no. Looks like it cannot, because copper is higher in the activity series. Copper is higher than silver, which means this reaction will not take place. So what do? You just write no reaction. Okay, that's what you do. No reaction. This reaction will not happen. You're not going to see nothing. Okay, you put some silver into this solution. By the way, if you're wondering, this solution is actually greenish blue, bluish green in nature. And you put some silver in there, and you'll notice that nothing will happen. The silver will not shrink in size. Copper sulfate will still be greenish blue. I'm gonna have to show you these things for real. All right, the next one. Aluminum reacting with nickel chloride, right? So I guess what you're gonna get is aluminum chloride plus nickel. Again, will this happen? Let's find aluminum and let's find nickel. Okay, so here's aluminum and here's nickel. Where's nickel? Nickel's right here. Oh, looks like it will. Aluminum is definitely higher than nickel, so this reaction will happen. You're just gonna have to make sure you balance it to make it complete. All right, magnesium and hydrogen gas. So you're gonna get magnesium sulfate plus hydrogen gas. Will it work? Well, let's see. Magnesium and hydrogen. So we have magnesium up here and hydrogen down here. Yes, it will. Magnesium is way higher than hydrogen, so therefore this reaction will take place. All right. Hey, looks like just one reaction here that's not going to take place. I'm going to add two more. Okay, I don't think this is enough, so I'm going to add part E. This time I have chlorine gas reacting with silver bromide. Okay, and I'm going to do one more too. Iodine gas reacting with sodium chloride. Now, remember, metal displace metal, non-metal displace non-metal. So in this case, you have a non-metal reacting with a compound. Consists of a metal and a non-metal. So this chlorine right here is not going to displace Ag. No, it's going to displace Br. The question is, will it? Will Cl displace Br? Now, you may be thinking, okay, I know the drill. I got this. Whoa. Wait here. I don't see Cl. I don't see Br. Well, that's because this is the activity series of metals and hydrogen. So you're not going to use the activity series of metals to do a non-metal displacement, are you? No, you're not going to do that. You're going to use the electronegativity values. Okay, so make sure you understand this very carefully. A non-metal will displace another non-metal if the electronegative value is higher. So you can think that, oh yeah, fluorine is going to displace everyone. Nobody's more attractive than fluorine. Fluorine will take your girlfriend, okay, or boyfriend, okay, because fluorine is going to displace every non-metal here that you'll see, because nobody's more attractive than fluorine due to his highest value in electronegativity. So remember that. So will Cl displace Br? Well, let's take a look. There's Cl right here. 3.2. Br, 3.0. Yeah, Cl will displace Br. Cl is more attractive than Br. So Ag says Come on here, Cl. Let's be AgCl, leaving bromine all alone. Now, you're not right entirely, okay? Br cannot be alone. Br exists as Br2. It's a halogen. Halogen, like hydrogen gas, cannot be by himself. Of course, you're going to have to balance this to make sure this is good. Great. How about the next question? Can iodine gas displace chlorine gas? I'm sure you guys know the trend, and you guys probably already figured out that the answer is no. Cl is 3.2. You are only 2.7. Okay? Cl is way more attractive than you're gonna try to displace me to hook up with Na? That's not gonna happen. Keep thinking, keep dreaming, because this reaction has no reaction. Because I will not displace Cl, because I is less electronegative than Cl. Not gonna happen. I love sodium's electron way too much for you to displace it. Ha! Alright, so that's single displacement. So make sure you know that not all single displacement will happen. If the displacement is between metals, make sure you check the activity series. If it's between non-metal, make sure you check the electronegativity. Alright, let's call it a day. Next lesson will be double displacement. Bye guys.